Okay, guys, let's start our third lecture from this Engineer Mechanics 1 Statics. So a few announcements before we start. I have been posting the recordings on the YouTube, so you can check it out. Homework 1 is due on Monday, so you have a few questions over there already to solve. And probably with those past two lectures, you can solve most of them. Today, we're going to cover the last problem of the homework as well. I posted my completely notes and affiliate notes on Brightspace, so you can check it out. The other problems that we didn't have time to finish during class. What else? One more thing, that tomorrow, Friday, if you are watching it before Friday, is the last day to add or drop classes, meaning if you want to continue in this class, okay, it's all good. If you feel that is not for you, doesn't fit the summer class, then the last day for you to drop and it's not going to count for you. You don't have to pay is this Friday, okay? Just keep it in mind. Is always good for to remind you about it. Okay, so let's go for it. In the name of the Father, Son, Holy Spirit, Amen. Direct, O Lord, we beseech you our actions by holy inspirations, and carry them on by grace's assistance, that every prayer and work of ours may begin always from you, and through you come to completion, through Christ our Lord. Amen. Father, Son, Holy Spirit, Amen. All right, let me share my iPad screen, and as always, please open your mic and speak if you have questions, or use the chat. I have here my cell phone on the side. I can always see the chat. If you have any questions, please let me know right away. Okay, guys, so first lecture, we talk about vectors. Of course, we talk about units, and then a little bit about vectors. Last class, yesterday, we discussed how to write a vector in 2 dimensions using x and y component, the Cartesian unit vector I hat, j hat. And then at the end of the lecture, I introduce the equilibrium equations, okay? Meaning that when we have a bunch of force applying an engineering problem, most of the time, at least in this course, we want to find the equilibrium for that body, for that particle, for that structure. We start with talking about particles. So last class, we talked about the equilibrium of a particle, okay? Where all the force have been applied at the same point, at the same particle, okay? Then we're going to continue this in a few more lectures, and then we're going to jump to talking about bodies with lengths, okay? But in today's lecture, I want to introduce to you 3D vectors and also equilibrium, okay? So it's going to be kind of a compact class here. We're going to introduce 3D vector, how we write 3D vectors, how we can write these 3D vectors in using a few points that we know, how we can find the x, y, and now z components of the 3D vectors, okay? And later on, the second part of this lecture, I'm going to talk about equilibrium of a particle in 3D dimension, meaning that all the force are going to be applied in one particle at the same point. However, now we're going to talk about 3D dimension, okay? Different from yesterday, that was 2 dimension. All right, so let's start. In 3D dimension, as we know, we have unit vectors I hat, j hat, but also k hat, okay? And it's used to give the direction of x, y, and z, okay? So far we have been working with what? I and j. But now, introducing the z-axis, we have k. And as you can see here, going to the right, as we have been using so far in this class, is a positive direction of x. Going up is going to be the positive direction of y. And then kind of leaving your screen, okay, leaving your notes is the positive direction of z. Okay, remember we talk about the right hand rule. Okay, if you put, like, I don't know if you can see how you see that in the screen, but if you do that, you can see positive, positive, and positive going towards you. Okay, so that's the 3 dimension that we're going to work. Okay, and then of course we're gonna have some force here. Let me take it here. Some force that is difficult to see right now, but we're going to have this y, x, okay, and some z dimension as well. Okay, z dimension. I should improve my drawing. So let me improve my drawing. So let's do like this here. Yeah, much better. Like this, and then the red one going like this. Great. So this is the force vector. Now we've zoom it with I, J, and K components, mean the X, Y, and Z components. Okay, so that's what we're going to be working for today's lecture. So consider the force, same force that I draw for you, okay, acting on the orange O and this system of X and Y, Z, okay? And as I show you, we have this force with X, Y, and Z component, and as you can see here, Fx, Fy, Fz. And Bruno, how can we find, okay, how can we find the components using the angle, using the direction? Because do you remember for 2 dimension, it was kind of straightforward. We have the coordinates here, we have the force vector, and then we have this angle. It was easy to say that one was cosine of that angle, the force, the magnitude times cosine, the other magnitude times sine of the angle. But what about 3D? Because 3D, okay, we have, as you can see here, this angle here, an angle between y, another angle between z, okay, and we can have the other supplementary, the complementary angles over there, okay. So which angle we're gonna use and how we're gonna write? Because one's gonna be sine, one cosine, tangent. What I'm gonna use, okay? And for 3 dimension, most of the time we use the cosine, meaning we're gonna write every single component using the cosine of the angle. Which angle? The angle between the axis that we want to find the component to the force vector. So as you can see here, from x to the vector, I have, let me zoom here, theta x. And what is going to be the component fx? Component fx is going to be the magnitude of f times the cosine theta x. Okay, as you can see right here. Then let's find the cosine of the angle that goes from y-axis to the force. And this angle we're going to call theta y. Then what is going to be fy component? F cosine theta y. Okay? So this, for 3 dimensions, is much better if you use different angles and always use the cosine. Okay? It's going to help us to find the direction of the force vector. So as you can see here, once again, from zx to f vector, what do we have? Theta z, and then that's how we write fz. Okay, so that's pretty much how we find fx, fy, fz for those components using the cosines. Okay, so those cosines, they are known as the following. Okay, let me highlight here. Direction cosines, because they're going to give the direction of the vector. If you have the angle that goes from one x to the vector, well, then we can find the direction of that vector, vector f. Okay? And the same way that we wrote a vector with I hat, meaning x component, j hat, y component, now we're going to write in 3 dimensions I hat, j hat, k hat, x, y, and z component. So as you can see here, okay, f is fxi, fyj, fzk. So if you have to write once again here, can I write like this? Okay, f cosine theta x I hat, f cosine theta y j hat, and f cosine theta z, sorry, z k hat. So right here we can write a vector in 3 dimensions, same thing. Okay, we can also have this. Okay, f is the common factor here, so let's do xi cosine theta y j cosine theta z k. Okay, so see what we have. We have now only the magnitude of f, and all of those are the direction cosine. Guys, and having all of those direction cosine, we can simplify one letter. That's what we call the following. Okay, we can write this expression here as the vector as the magnitude, okay, times lambda, okay, times this lambda. Bruno, and what is this lambda? This lambda is called unit vector, okay, unit vector, lambda, okay, unit vector. And once again, what is f? Is the magnitude. And what is the unit vector, Bruno? It's right here on the bottom, okay? Unit vector. Let me highlight here for you. That's important. Unit vector. A vector whose magnitude is equal to 1, meaning that the magnitude of this vector is 1. Okay, same as the I hat, j hat, k hat. Okay, why we have this unit vector? Because this unit vector, take a look, its direction, okay, is the same as that of f. Is used to represent direction. Let me highlight this here. Okay, represent direction. Meaning that once we combine these direction cosines, now we have this unit vector that his job is to tell you, A, the force vector is going to this direction. Okay, is going to this direction, and then we multiply by the magnitude, then we have the full vector. Okay, full vector F. So for example, right here, let me try to show you in maybe do my best to 3 dimension, but at least you can visualize here. This right here would be the unit vector, lambda. Okay, lambda just unit magnitude is equal to 1. Okay, it's telling you that a vector f is going to this direction. Once we multiply times f, what are we going to get? F vector. Okay, so the job of unit vector, and that's pretty much what we need to find. We need to find the unit vector because we need to find the direction of the vector, of the f vector, of the force vector. Okay, so the job of this unit vector is just to point, hey, the force vector, this tension vector, whatever vector is going to this direction. Okay, and once we have unit vector for one vector, another unit vector for another vector, so we have now different directions. Now we can simply come and sum them and find the resultant. Okay, so that's why unit vector, this lambda, is so important in 3 dimensions. Okay, Bruno, okay, I see. And then I can kind of visualize that unit vector comes from direction cosines. We need to find the angles between x component and the force, okay? But how can I maybe simplify this method to find? Maybe I'm not gonna, it's not so easy to visualize the angles, this 3D dimension, and how to find those angles. Maybe I'm trying to find the resultant. How can I do that? Okay. Well, so that's why let me introduce now, and maybe you already know that. Okay. How can we define, okay, the force defined by its magnitude, And how can I define when you're working in a coordinate system in a problem that we have dimensions, okay? How can I write this unit vector just using dimensions or points that I know from the problem? Because sometimes the angle is not gonna be given to you. We have some points. Hey, this start here and finish there. Okay, this the orange is here and 0, 0, but then we have a force apply and this coordinate x blah blah blah, y blah blah, and z blah blah. So we have some points in your system. And how can I write a force vector or a vector using those points? Okay, so that's what I want to talk right now. So let's take a look in this problem here. We have 2 points, the point M and the point N. Okay, point M, the coordinates are those, okay, x, y, x1, y1, z1, and N are those. So let me write this so we can just visualize the coordinates of those points are the following: x1, i1, z1, and then x2, y2, z2. All right. So what I'm trying to do here, once again, I'm gonna try to write this vector force that goes from M to N. Okay. What is this vector force acting? Remember, guys, I think I mentioned to you the first lecture, line of action. Okay, this force is in this line of action. Okay, so what I need to find is what is this direction? What is the direction of this line of action? Okay, what is the direction of this line of action? Okay, so that's what I'm trying to find. I'm trying to find this direction. And later on, okay, I'm going to multiply this direction to the magnitude, so I'm going to find f. Okay, but first I need to find the direction. What is the direction of this line of action where the force vector is on the top? Okay, that's what I'm going to try to find. And how can I find using 2 points? Okay, so I can find the unit vector by doing the following. I have 2 points. Let me already give to you the equation. Lambda is defined as the following. Okay, the vector mn, okay, vector mn divided by the magnitude of mn. Okay, I have, once again, guys, I have 2 points. I know 2 points in this line of action. I know these 2 points. So let's find, using those 2 points, their direction. How can I find it? Well, I'm going to get this vector mn, meaning starting from m, going to n. Okay, what is this vector? And what is the magnitude of this vector? Okay, by doing that, I can find the direction. Now, Bruno, how can I find a vector using 2 points? I don't know if you remember math, but I'm going to review here for you. Right here, a vector using 2 points is going to be, if the vector is going from M, okay, starting from M to N, okay, vector M to N, I'm going to have these coordinates of N minus M, okay, my finish point minus the start point. Meaning that, what's going to be this one? X2 minus X1, Y2 minus Y1, Z2 minus Z1. Those are going to be my vector, okay, Mn. Okay, my vector Mn. At the end, we can simplify saying, okay, this is dx I hat, dy j hat, dz k hat. Okay, so the difference between x2, x1, we call dx. Difference between y2, y1, dy. Difference between z2, z1, dx. So far, so good? Okay, all good? Any questions? Okay, keep continuing. Now, I know now how to write vector. Okay, I remember from math. Okay, this is how I write vector using 2 points. 2 points. Now, Bruno, you said something about magnitude. Magnitude. Okay, how can I find this? So let me write here just for you. Vector mn divided by the magnitude. Magnitude mn. Okay. How can I find the magnitude? How can I find a magnitude of a vector? Remember in 2 dimensions what we did? X squared, y squared, square root. Because we use the right angle triangle, that equation. Here is pretty much the same. Okay, the magnitude, let me write it here, magnitude, which allow me to write like this now. Okay. dmn. Allow me to write the magnitude like this just to make distinction between 2 dimension and 3 dimension. Okay. The magnitude is going to be the following: square root of dx squared plus dy squared dz squared. Okay. This is the magnitude of a vector. Okay, 3-dimensional vector. Now, coming from the unit vector, coming to the unit vector, how can we write this unit vector lambda? Well, this is going to be, can I get the orange line? Dx I hat, dy j hat, dz k hat, divided by square root of dx squared, dy squared, dz squared. This is going to give you the direction of that line of action, meaning lambda, the unit vector lambda. Okay? Because what we're doing, we are dividing the vector mn, which is this vector from m to n that we know that exists on that line of action. We are dividing by the magnitude, meaning we are just doing a unit vector from that direction. Okay? Bruno, and this is going to be a vector? Yes. Why? Because, guys, remember, this is I hat, j hat, k hat. We cannot, again, we cannot sum them together. They are different. They are components of a vector. However, those here on the bottom, I'm just talking about dx, dy, dz. I'm going to square them, square, square. I'm going to sum them together. I'm going to take the square root. And the result of this on the bottom, I'm going to divide by this, blah, blah, blah. Divide this and divide this. Okay. At the end, I'm going to have something I hat, another thing j hat, another thing k hat. Okay. So that's what I'm going to have. At the end, once we get the unit vector, okay, how can we write the f vector? Okay, the force vector that we are trying to find. We are trying to find this force vector. Force vector. How can I write it? Okay, is the magnitude times lambda. So this f vector is going to be the f times what is lambda once again? dx I hat, dy j hat, dz k hat, divided by dx squared, dy squared, dz squared. Okay? Let me simplify it to you. Maybe you can visualize better. Magnitude divided by the magnitude of the force vector divided by the magnitude of these 2 points, okay, of this vector mn times dxi, dyj, and dz. Okay, so if I have to write equation for f vector in 3 dimensions, this is it. Okay, using 2 points. Once again, using 2 points, which is going to be most of case for us in this class. And when we're working, we have some coordinates. We're going to use those coordinates to help us find the direction. Okay, sometimes it's more difficult to find the angle in 3 dimensions, okay? Those 3 different angles that we mentioned for the cosines. Any questions, guys? Please write in the chat or tell me okay in the chat. Sounds good, anything like that. Okay. By the way, every time that you going to type something in the chat, please type on the general chat, okay, not the DM to me, because I can see just the overall chat. Brian just got here right now. It's okay, Brian. We just talk about vector in 3 dimension. Okay, I'm gonna do a problem right now, so hopefully you can follow. If not, you can watch it later. Okay, this first part. But we're gonna do a problem right now where I'm gonna show all of this. Okay. Just to tell you that from this dx, dy, dz, okay, I can simply, okay, find the cosine of those angles. Okay, so in other words, what we are doing here, once we divide this magnitude by dx by this magnitude, what we are finding the cosine of theta x, because it's the direction. Once we divide this magnitude, okay, dy by this magnitude, we're going to find cosine of theta y. Okay. Once we divide dx by this magnitude, we are finding cosine of theta x. Okay. So using 2 points is going to go to the same way as using the cosines. Okay. But once again, most of the problems we're going to work is you're going to give coordinates of points in a system. In a system. So that's what we're going to use here. Okay. Just because I took this from the book. So D here is my DMN. Okay. This D is the DMN. Just to clarify this. Okay, so let's put this in a problem so we can visualize how to write 3-dimension problems, the coordinates and also the vectors. Okay, I have just one problem here, and then we're gonna get all this knowledge and then go to the equilibrium equations. All right. Okay, so let's see. We have this tower with this cable, both at A. The tension on this wire in this cable is 2,500 newtons. And we need to find the components Fx, Fy, and Fz of the force, okay, acting on the bolt. And then if we have time, we can find the angles. Okay, but the angles, as I show you here, is just using this equation. Let's see if we have time. I really want you to pay attention how we find the components, okay, because this is the most important part for this problem and what we're going to use. Okay, so let's start. Let's remember, okay, my F is F times lambda. Okay, this is the magnitude of F, and this was already given. What is it? 2,500, okay, newtons. So what we need to find now is the direction. Okay, which direction, Bruno? Well, where is the force vector? I have a tension on the bolt. So my tension, okay, on the bolt right here. This is my F. Let me make it bigger. Right here. This is my F of 2,500 newtons. What we need to find now is this one here, lambda. Sorry guys, I like to keep using the same color. So let me do it again. This is F because I use blue over there. Newtons. And this is lambda. Okay, this is lambda. All right. So we need to find lambda. Right here, well, I have one point A, another point A, B. Okay. So I'm going to use those 2 points to find the unit vector. So where should we start those problems? In every single 3-dimension problem. Okay, I'm going to give you some steps. First step, right here. Okay? First step, coordinates. Okay? I need to find the coordinates. Coordinates of what? Well, the 2 points that I'm going to use to define this orientation, this direction. So I'm going to write the vector AB, okay? Because I have points A, B. And they are known, okay? Take a look. I have here the X, Y, Z, okay? Something I have and Y, okay? I just have to figure it out. What are those coordinates? Okay, so let's figure it out. A. What are the coordinates for A? Okay, and this is, I understand this is sometimes difficult to visualize in 3 dimensions. Maybe it's your first time working in 3-dimension problems to visualize the coordinates. So let's go it slowly. X, guys, X is right here. X vector, X component. Okay. What is X? Well, X should be the distance from the orange to that point. This distance here, how much is this distance? 40 meters. Okay? I hope you're, when I ask, I hope you answer the question, even though you're over there in your house. Okay? 40 meters. Wow, 40 meters. What is Y? Right here is difficult to see. But because I don't have anything showing the distance here for A, okay, the Y direction looks like, okay, if I remove this, maybe if I remove this one, you're gonna be able to see, okay. This is right on Y0, okay, kind of on the floor, same direction. I don't have anything here, okay. Remember, this is 3-dimensional. You need to visualize this one. And what is the dimension or the coordinate for Z? This is, remember, the right-hand rule, Y positive is going this direction. Z positive is going to this direction right here. Where is this bolt? This bolt is, take a look, 30 meters. 30 meters coming to the front or to the back? Going to the back. 30 meters going to the back, meaning that this is a negative direction. 30. Bruno, why is 40 is positive? Because 4 is going to the positive x direction. 0 and then 30 is going to the negative z direction. What about B? Well, B in x was right here in the orange. Okay? 0. What about Y? Y, now I have something in Y. 80. What about Z? Well, Z is right here again, in the orange. Okay? 0. Any questions about the coordinates, guys? write down in the chat or let me know right now. Everybody?
I have a question about
Yes.
the 31. Is this like
Okay.
when you can decide which which one is like negative and which one is positive? Like you can decide the direction, or is it something fixed?
No, it's something fixed. It's something fixed because of the right-hand rule, okay? So most of the problems, we're gonna work with x going to the right, y going up, and z coming towards you, okay? Uh, it's just something fixed that at least we're going to use in the class. Of course, if you are working by yourself, not other engineers, maybe you can just follow your own axis. Okay, this is okay. But because you're in the same environment and just following um, what is predefined, we predefine that we're going to use the right-hand rule, meaning that x positive going to the right, y positive going up, and z coming towards you.
Okay, thank you.
Okay. Yeah, Brian said anything that's on the opposite side of the base coordinate plane would be negative. Um, yeah, when we are talking about the z direction, yes. When you're in the back, yes. Okay, z direction, yes. For this, okay. But the others are good, like the positive for x, positive for y, okay. And we have more problems for you to visualize, getting better on visualize 3 dimension. Great. Thank you for the questions, guys. Now, what do we need to do? Well, let's now, because we have the coordinates, how can we define, once we have the coordinates, how can we define lambda? Okay, so let me write here. Lambda is what? The vector AB divided by the magnitude of AB, okay, which is, okay, B minus A divided by the magnitude. Okay, the coordinate B minus A divided by the magnitude. So let's find what is B minus A. Once you come here, B minus A is what? 0 minus 40, 80 minus 0, 0 minus 30. Okay. What are we going to have? B minus A is going to be negative 40, positive 80, and this positive 30. Okay. So this is going to be dx, this is going to be dy, this is going to be dz. Okay. And let's take opportunity and do the DAB, meaning the magnitude. Square root of minus 40 square plus 80 square plus 30 square. Okay. What is this magnitude? Once again, guys, please take your calculator, try to type, get the same number as me, okay? And see if you are good using the calculator that you have. Okay, for this one, I got 94.34 meters. Okay. Now what I'm gonna do, come back here. This is negative 40 I hat, positive 80 J hat, positive 30 K hat, divided by 94.34. 94.34. So this is my unit vector. Okay. I'm gonna just do one calculation at the end. So let me leave the unit vector like that. Of course, you can divide 40 divided by 94, 80 divided by 94, 30 divided by 94. Let me do this at the end when I'm not only trying to find lambda, I'm trying to find the force vector. And what is force vector? F times lambda. Okay? And guys, please pay attention. Okay? Once we start having more and more vectors, the most mistake that I have from students, excuse me, is forgetting about this F, forgetting about the magnitude of the force, okay, and working only with the lambda, okay? The force vector, we need to multiply the magnitude, meaning we have at the end 2500, negative 40i, 80j, 30k, divided by 94, 34, okay? So let me do this calculation at once. Okay, try to do this calculation there right now. 2500 times negative 40 divided by 94.34. Then 2500 times 80 divided by 94.34. And keep going. Okay, in my notes, I have those results. You can check it out. Okay, and as I said, those are going to be a vector. I'm not going to sum them together because it's I hat, j hat, k hat. Those are the components of F vector. Which vector? This force right here. Those are the components of that vector. Any questions? Let me know. See if you can get the results. If you're calculating, if you're copying it. So let me just simplify. So what I did was, okay, I start here. Right. A, and what I did was B, C, then I come here D, and finalize here E. Oh, I just said. See if is everything okay. All good? Awesome. Great. All right, great. So let's keep going. Okay, right here, as I said, it asks for the cosines, the angles. But then it's just applying these equations here. Okay, I'm gonna leave it to you. I'm gonna complete it later. But just applying these equations with the D, and then I think it's very straightforward. So let me go to the other part, which is the equilibrium, which is much more important than finding those angles. Okay, so I'm gonna leave this part here for you to complete later. I will complete and post to you. Okay? But this part is the most important part I want you guys to understand. Okay? I want you guys to review it every single time. How to find this force vector using 2 points. Okay? And pretty much that's what we're going to do right now. Because now we go for equilibrium, where we're going to use force. Now, right now, guys, this was only one force. One force. We're going to have to do this for many more and one problem only. Okay, so please, you have to get it the step by step. Okay, let's go for equilibrium. Okay, and then let me introduce, maybe we can just finish today without the the break. Okay, let's see. Let me zoom here. Equilibrium. Okay, let's talk about now equilibrium. Okay. as I said, most of the time here in the statics, we want the body to be at the rest, in equilibrium, okay? And in 2 dimensions, we have two equations of equilibrium. Why? Because we have x and y component. Now, in 3 dimensions, what we have? 3 equations of equilibrium. Of course, x, y, and z. Meaning that once we sum the force vectors, we sum their x component, y component, z component, they should be 0. Okay, that summation. Okay, and then just once again here, this is the expression for a f vector. Okay, is the magnitude times the lambda, and this is how we define just right now. Okay, so what is the step-by-step to solve a problem in 3 dimensions, to find equilibrium in 3 dimensions? Well, first of all, draw the free body diagram. Okay, draw the free body diagram, or sometimes I understand that, for example, here, this problem is much easier for you to visualize because the drawing is already there. So when I say draw the free body diagram, let's draw the force. Okay, let's highlight the dimensions. Let's see what we have. We're gonna have this one here. We're gonna have some weight. So let's put the force, the weight vector over there. Okay, so let's put something for us to visualize what's going on. Okay, write the force into Cartesian notation showing the x and y component. What is that? Well, we have the force. We're gonna have the force. We're gonna have to write what we just did in y, j, and k. Okay, pretty much the second step is to do all of this. To the end, we have I, j, and k, I, j, and k, I, j, and k for each single force. Okay? Third step, of course, apply the equations of equilibrium. Okay? Sum of the force and x should be 0. Let's sum all the I hats. I hat. Okay? And at the end, solve for the unknowns. Okay? Solve for the unknowns. And we have 3 equations of equilibrium, so we can have up to 3 unknowns. So that's what we want to find. The 3 components of a single force, the magnitude of 3 force. Okay? So what do we want to find? Let's see, depending on the problem. Okay? So this is the step-by-step for solving those problems. Free body diagram, XY components, equilibrium equations, and then solve. Okay? Okay, let's go for it. Okay. I'd love to see your excitement to solve the problems. Let's see. First step. Let's start with the first step here. What is the first step? Draw the free body diagram. Okay. Let's see what we have. Let's understand the problem. Okay. We want to find the force in each cable. Okay. Where are the cables? Well, I have cable AB, cable AC, okay, and cable AD. Okay, I have force tension on those cables. Okay, tension being applied on this point A particle. All good. Okay, got it. What else? What else? Let's draw it. Okay, let's draw it. Force here. Force AC vector right here. AB, and right here AD. All good, force vectors. Okay. Force in each cable used to support the 40 pounds crate. Okay. So we have 40 pounds here. Okay, different from the international unit that was given the mass. Every single time that we talk about pounds, if I'm not saying pound mass, is always the pound force. Okay, meaning that this is already the weight. Okay, this is already the weight. Pounds is already pound force. Okay, so this is already the weight vector. Né? Okay, so we don't need to worry about multiplying these to anything. Okay, I have the weight, another vector, 3 vectors over there. All right. So what I need to do now, I need to write the force into Cartesian notation in XY component, okay? Now start the things. Let me write FAB, FAC, FAD in the Cartesian notation, okay? So how I'm gonna do it? Oh, I have a little bit of space here, so let me put it here. First step, coordinates, okay? Please stop me if you didn't get any, you don't get anything, okay? Which points do we have? We have point A, point B, point C, point D. Okay, so let's see if we can get um, all the same here. Point A, point A. I think this is okay. Because everybody understand this is 0, 0, 0. Point B. Okay, nothing starting to visualize. B, I don't know if you can see that, but you see this is saying is going to that direction. Okay, meaning that B is on the left side of X. Okay, B is on the left side of X. So this is going to be negative 4. B is going up, okay, all the way there, the way here. Okay. Sorry, is the same direction here, but it goes to there. That's why 3-dimension is a little bit tricky to visualize. So this is going to be 8, okay? So this is the distance to this, but this is not going up. This is just going to the side, okay? Just going to the side. So it's 8 feet. And then Z, right here, okay? And positive Z is this direction, going to that direction is negative Z, negative 3. What about C? C, it's same thing here, okay? In X, I have 4. However, as you can see here, this plane divide the right-hand side and left-hand side. Point C is right-hand side, meaning positive 4. Also, the dimension Y, the distance is 8. When this plane here, okay, but it's 3-dimension here. Okay, this is the same plane. Here you can visualize, same plane. So this is 8. And then Z, okay, negative 3. Once again, going, this is positive, this is negative Z, okay? And on this side, this plane here on the back is negative Z, okay? Now, you can ask me, Bruno, what about D? What about point D? Well, guys, this is a special case because D, okay, what is X? If you have to write D, just write here, D. X, 0. It's right here, the orange. What is Y? 0. And what is Z? Well, Bruno, I don't have Z. I don't have Z. I cannot see Z here. For this problem, it's totally fine. Why is totally fine? Because, take a look, where this FAD is. FAD is totally on the Z direction. It's totally on Z direction, meaning it only has Z component, okay? Z component. So we don't need a point to define the direction of FAD. We already know the direction of FAD. FAD is going to the Z direction, okay? Z direction. Same as Y, okay? What is the direction of, not Y, sorry, W. What is the direction of W? What is the direction of W? Oh, sorry. Just a second. I just this is Z, no, this is Y. What is the direction of W? Going down the Y direction. Going down the right direction. What does it mean? It means negative Y direction. Okay, so for FAD and W, we already have the direction of those. Okay, the direction of those. Okay, so what we need to find is FAB, FAC. Okay, FAB, FAC. So let's do that. Okay, let's do that. Okay. Second, Cartesian notation. So far, so good. B vector. How can I define FAB? FAB times lambda AB. Lambda AB. And what is lambda AB? B minus A divided by DAB. Okay. Can I save some time and space and do it right here? FAB, the magnitude, we don't know. That's what we're trying to find. What is the magnitude? What's this force? Okay. FAB. And do it right here like this. What is B minus A? Minus 4 minus 0 plus 8 minus 0 G plus minus 3 minus 0 K. This is B minus A. Divided by the magnitude. Minus 4 minus 0 square plus 8 minus 0 square plus minus 3 minus 0 square. Okay, guys, right here I just wrote everything at one place. Okay, of course you can just get another step and do the B minus A separately, because here I want to save some space. Okay, find the magnitude, the other side. You don't need to type all of these in at once in the calculator. Okay, you don't need to do that. FAB is FAB times negative 4, positive 8, negative 3. Divide by, once you do this calculation, 9.43. See if you can get 9.43. At the end, I have 0.42 FAB. I had positive 0.85 FAB J hat. And the last one, 0.32 FAB K hat. See if you agree with me, see if it is all good. If you are trying to type in the calculator, please, if I have a typo, let me know, okay? Sometimes I solve it, I have my notes, but it's all good. If I have a typo, just let me know. We can check the calculation. Okay, so this is FAB. Okay, I found FAB components. Now, what about FAC? Because FAC, I also have to work with the Cartesian notation. Okay, with the lambda. Can I? This is FAB. Let me put this maybe FAC here. FAC once again is FAC magnitude lambda FAC or lambda AC FAC of um, C minus A. C minus A, I'm going to put it here already. 4 plus 8, negative 3, 4ij, positive 8j, 4i hat, 8j hat, negative 3k hat. Okay. Let me already go here and do that. Calculation is going to be the same as on the top. Okay, because they're the same. The only thing is this negative. Okay, that negative. And at the end, going to be positive 0.42 FAC, positive 0.85 FAB, J hat, I hat, negative 0.32 FAC, K hat, a typo here, we'll just copy and copy AC. Sounds good. And just to write here, for you to have FAD. What is FAD? As I said, FAD magnitude K hat. Okay, because that's the only component that I have in FAD. Also, what is W? Negative 40 B hat, because this is the only component that I have in W. Sounds good? My last step, my last two steps here, apply the equilibrium equations and solve for the unknowns. Okay? Apply equilibrium equations and solve for the unknowns. What are those equilibrium equations? Sum of the force in X should be 0. What I have in X? This one here, this one over there. It's going to be negative 42 FAB plus 0.42 FAC should be 0. Cannot solve, but I can write FAB same as FAC. What about this sum of the force in Y? What I have in Y? 85 FAB, 0.85 FAC. Don't forget the W. So I have 85 FAB plus 85.85 FAC negative 40 equal to 0. And I get this equation here. There, so I'm gonna have 85 FAC plus 0.85 FAC should be equal 40 equal 40. At the end, FAC is, let me see what I have FAC here, 2353 pounds. Okay. And if this is 23, well, FAB is the same, 2353 pounds. Okay, the only one I'm missing FAD, which I will find, okay, sum of the force. This yellow is not that good, right? Let me see if I can change this yellow. Pink. Let's use pink. Sum of the force and Z should be 0. What I have in Z, 32, negative 0.32, negative 0.32, and this one over there. So negative 0.32 FAB, negative 0.8232 FAC, plus FAD should be 0. Okay, well, now we have this one, that one. You're gonna find the FAD, you're gonna calculate at the end. My calculation here, I have 15.06 pounds. Oh, 6 pounds. And that's it. Okay, I found the force on each cable. How does it sound? Good? Let me put it here so you can see everything. Here. All good? See if you agree, see if your calculation is the right track. See if you can visualize those coordinates. Yeah. Please, if you are watching it, the recording, mail me your questions. Okay. Do not finish a lecture with questions, especially this online environment. You can replay, go again. If you don't understand, please reach out. Please reach out. Okay? I'm completely available to talk to you, help you to understand. Okay. Looks like it's all good. Let's go for the next one. Everybody's already copied. I believe so. Okay, we have, let me see what we have. 2 more problems. Actually, okay, not be extensive, and because you guys are doing a good job. I'll do the problem number 2 now, and I will leave problem number 3 for you to have one more problem to work, because I believe in the homework we just have one problem. So with this one, 2 problems for you to work by yourself. Remember to, if you have any questions, let me know, or you can find another problems as well. Okay, so let me solve the second problem and leave the 31 for you to work on it. And again, I will solve it and post to you later on. Okay, let's talk about now this second problem. Well, all right. 200 kilogram cylinder is hung by means of 2 cables. We have 2 cables here. Cable AC, that I see over there. Cable AB, okay? Cable AC, cable AC, cable AB. Attached to the top of a vertical wall. Okay, we have this wall over there. So they are attached over there. Right. Horizontal force P perpendicular to the wall. Hold the cylinder in the position show. So the cables are there. I just apply a force probably with my hand just to move the cylinder a little bit, not a little bit, but 1.2 meters, looks like, from the wall. We want to find the magnitude of this force P, okay? And the tension of in each cable. Okay, so we don't know the tension in this cable, the tension that cable, and the force P to move this cylinder 1.2 meters from the wall. That's what we want to find, okay? So let's go and solve it. First, let's go here and see. Draw the free body diagram. Later on, write the force in Cartesian notation. Okay, free body diagram. What do we need in free body diagram? We need the force. Okay, we need the force right here. Let's call this force AC. Okay, right here, force AB. Okay, P is over there. Well, I'm missing my coordinates. Okay, I need to find the coordinates. And guys, let me use the red one. It's much easier if you put the coordinates, the orange point, where the force are being applied. Meaning that, see if you agree, can I come here and instead of using the wall as my coordinate, can I write the coordinates coming from point A? Okay, starting from point A? Yes, I can. Okay, so right now my orange point is A. Okay, and the wall, for example, the wall, see if you can visualize, the wall is on the left side of X now. Okay, the coordinate is here. Okay, coordinate is here in front of the wall, and the wall is behind the coordinates. Okay, the panel of this wall is over there of X. Okay, the negative direction of X. Can everybody see it? It's much easier to find those points if the orange is on the point that the force are being applied. Okay, so far so good. All right, so coordinates. Okay, remember first one, coordinates. Let's find those points. Which points? A, B, and C. Okay, well, why is it so easy? A, because it's the orange point, 0, 0, 0. 0, 0, 0. What about B? Now, because I put the coordinates here in front of the wall, B is in the wall, okay? Over there. So negative 1.2 meter. Why negative 1.2? This is 1.2 is the wall, direction of wall is 1.2 behind, meaning 1.2 the negative direction of X. So this is negative 1.2. What about Y? Okay, what about Y? So give me some time. Should Y be 12? No, should not be 12 because remember how I define my my coordinates, okay? So Y should be this to that one, okay? This point to this one here. It is not 12. I know how much is this part only. Okay, take a look here. 2 meters. So if this is 2 meters, how much is this one? 10 meters. Okay. What about Z? Z starting from here to there, okay? Meaning these two points, it is going to the Z direction, so positive. And C in this case is okay, is similar, negative 1.2, positive 10, okay? And I have a little bit tricky here, do not confuse, not 8, now it's 10. 10 going negative direction, so negative 10. Negative 10. Okay? Let's write FAB. So FAB. FAB is going to be, okay, here, once again, I'm going to go straight to the point. I'm going to go straight to the point. You can do the middle steps, intermediate steps, and check it out. FAB, negative 1.2 I, positive 10J, plus 8K, divided by 1286. Bruno, where you got this? Well, remember this is B minus A, B minus A. And this is good because A is 0. So it's all the same here. Okay, but in reality, this is B minus A. And what is this? This is 1.2 squared plus 10 squared plus 8 squared square root is going to be 12.86. Okay, I'm going to just going to straight to the point here. Straight to the point. Negative 0.09 FAB I hat. Positive 0.78 FAB J hat. And positive 0.62 FAB K hat. Let me give a few seconds for you to visualize, to see. It is okay if I go straight to the point once again. If I skip the calculations. C minus A. C minus A. And C minus A. 1.2 square plus 10 square plus 10 square. Square root of that, 1419. Negative 1.2 divided by 14, negative 0.085 FAC. 10 divided by 14.7 FAC. 10 divided by 14, negative 0.7 FAC. What else I have of vectors? P vector. Just P I hat, x direction, and oh, I forgot to draw it. Please let me know if you see I forgot something, okay? W vector. 200 kilograms times 9.81. 1962 newtons. Okay, so W here is going to be 1962 newtons. Sorry. The direction of it, negative 1962 J hat. Then this is newtons. Okay, so I have right here 1, 2, 3, 4 vectors. And what should I do? Sum of the force in X should be 0. Actually, let's do the colors once again. I like the colors so we can follow somehow. X equals 0. Okay, so we have negative 0.09 FAB, negative 0.008, no, 85 FAC plus P equals 0. But right here, I cannot solve anything. I have 3 unknowns, 1 equation. So let's go for another one. Sum of the force in Y should be 0. Y, 78.7, and this one here. Right here, 78 FAB, 0.7 FAC, negative 1962, 0. Right now I cannot solve it. Let me write this third equation before I decide which one I'm going to substitute in either one. Okay, it's always good if you write those equations, so maybe you can find something easier to work. Let's see for Z. Z, we have 62.7. Okay, so this is going to be positive 62 FAB, negative 0.7 FAC equal to 0. So this one much easier for me to substitute, write one in terms of order. FAB is 0.7 FAC divided by 0.62. FAB is 1.13 FAC. Okay, so this is my equation number 1. Okay, and if I come here, substitute number 1, I will leave it to you. I'll find FAC 12,440.67. Okay, this is my number 2. Then I will come here, using number 2, I will find FAB 1,401.96 newtons. That's FAB. Number 3, I will come here. This is 3. This is number 2. You're going to substitute this one here, and we're going to find P, 231.63 newtons. That's P. Okay, so let me give you a few seconds just for you, if you're trying to calculate, see if you can get those numbers. Please pay attention right here. Right here. Actually, because we still have time, let me just do this so you don't forget this one here, okay? The same as I mentioned yesterday, do not forget the 0.78, okay? We are substituting just FAB, okay, just FAB. And for this one, what was FAB? FAB was 1.13 FAC plus 0.7 FAC equal to 1962. Okay, and then you're going to multiply. Let me do this. 0.78 times 1.13 plus 0.7. Okay, at the end, I will have 1.5814 FAC 9262. Then divided by this, what I wrote was FAC 1240.67. That's it, yeah, newtons. Okay, you're gonna multiply this one. Any questions, guys? Any questions? Please let me know. No questions? Everybody good? I think the only trick here is finding the coordinates. Once you find the coordinates and you know the steps, it's going to be just following these steps. Equilibrium equations, the same as in 2 dimensions. Okay, as you saw, most of the case, we're gonna have a system of equations. You just have to work with math. So it's more like math style in order to find the force to keep in equilibrium. All good? So as I mentioned, I will leave this problem number 3 to you, okay? Because this one is good. I want you guys to work because we have like 3 coordinates, 3 force, different coordinates, A, B, C, and D. So you can work from there, okay? This one, let me just mention the following, okay? This one, you have a few options. Okay, you have a few options. I think someone asked me about the positive Z, it was okay, just always that way. I said yes. But one thing that you can kind of move around are the orange, the coordinates, orange of the coordinates, where your orange is starting. And this problem is already given to you. Okay, it's already given to you. As you can see, in this particular problem, the orange here is not starting from point A. It's starting right there where we have mostly of those, all of those bolts, or anyway, those bays here where we have the orange. They are in the same plane, okay? Meaning that this Y for B, C, and D, they're going to be 0, okay? Bruno, can I move this orange to this one here and have like this and that and right here? Yes, you can. Okay, but now you're going to be working with Y negatives. All of them negative Y, okay? But then I will get different answers, we get different answers for the fours? No. You're going to get the same answers. Okay? So it doesn't matter where your orange is starting. Okay? Doesn't matter. If you're going to get positive or negative y, okay, or y is going to be 0 or negative something. Okay? At the end, it's going to work fine. Okay? If you follow your procedure. All right? Myself, I'm going to solve this problem here and send to you, okay, post to you. Keeping the orange right here, and then I'm going to work with y0 here, y0 there, y0 here. Okay? And this A is not going to be as this one here, 0, 0, 0. It's going to be something else. This is not going to be the same as this 0, 0, 0. It's going to be something else. Okay? So it's a good problem if you keep the orange over there. Okay? Just so you can work with A without being 0, 0, 0. So you can do some extra calculation and see if you are all good with the problem. All right, guys. Okay, so if you are watching it online, please review the other 3 classes, and then we can keep going next week. Okay. Well, because this was just intense class, just showing here a few things before we finish actually as a review. Okay, I'm not going to do any problem for review, but I would just want to mention a few things that I really want you to visualize. One of those being the 2D equilibrium, okay? Being able to find those equilibrium and what else? Applying these equations. We're going to work a lot with 2 dimensions, okay? Much more than the 3 dimensions. So this right here, to find which one is sine, which one is cosine. Okay, I really want you to pay attention on that. Okay, if it is something for you to keep on mind during this weekend, how can I write the components of a 2D vector using sine and cosine? This is very important for us in this class. Okay, of course, the direction of being positive or negative is always important. Okay, other than that, the 3-dimensional derivation today, the unit vector, the lambda, and just talking about the first lecture, actually not the first lecture here, the note, but the first lecture about the units, okay? Pay attention to the units. Very important for us. Okay, so that's how I want to finish the class. I wish you guys a very good weekend. Okay, let me know if you have any questions regarding the homework, email me. Tomorrow, today, during the weekend. I will make sure to answer you by Monday. Okay? Let me stop the recording. So if you have any questions, you want to stay a little bit, feel free to do so. Right here, stop recording. Where is it?